Fine. Let's start. Number 10. The fourth spatial dimension. Hold up your hand and look at it. 3 directions define everything it can do. Left and right. Up and down. Forward and back. That's it. That's the whole menu. Every motion you have ever made, every place you have ever stood, every object you have ever touched, lives inside those 3 directions. We call it 3-dimensional space, and it feels less like a theory and more like the floor under reality. Total. Complete. Nothing left over. Now imagine there's a 4th direction. Not time. A 4th direction of actual space, pointing somewhere that isn't left, isn't up, isn't forward, and isn't any combination of those 3. A direction you cannot point at because your arm can only move through the 3 you've got. This is where your brain hits a wall, and it's supposed to. Your brain was built by 3-dimensional survival for 3-dimensional problems. It has no reason to picture a 4th way to move, but mathematics has no such limitation. And mathematics says the 4th direction is not just allowed. It's almost boringly consistent. Here's the way in. Picture a flat world, a sheet of paper, and living on that sheet, drawn in ink, a little 2-dimensional creature. He knows left, right, forward, back. He does not know up. Up is not a place he can point. Up is not even a word that means anything to him. Now you, a 3-dimensional person, lean over his paper. You can see his whole world at once. You can see inside his little square house without opening the door, because from above, the walls don't cover anything. You can see inside him. His insides are just lines on a page, and you're looking down at all of them. And if you wanted to, you could reach one finger down into his sealed body and lift something out. From his point of view, an object simply appeared inside him from nowhere and then vanished. No wound, no opening. Just there and then gone. Now take everything I just said and move it up 1 floor. You are the flat creature, and something that lives in 4 spatial dimensions is leaning over you. To a 4-dimensional being, your sealed body is an open book. Your skin doesn't cover anything because it can look at you from a direction your skin doesn't face. It could see your beating heart without an X-ray. It could reach in from that 4th direction and lift the heart out and close nothing behind it, because there was never a hole to close. To you, it would look like your chest was untouched, and your heart was simply gone. And that's the polite version. There's a stranger one. A man named Charles Howard Hinton spent his life trying to teach people to picture this. In 1888, in a book called A New Era of Thought, he gave the 4-dimensional cube its name. He called it a tesseract, a word you've probably heard without knowing it came from a Victorian mathematician quietly obsessed with a direction none of us can face. His essay asking, "What is the 4th dimension?" came out in 1880, 4 years before the famous little novel Flatland made the same idea famous. And here's the twist that turns the whole thing genuinely unsettling. If a 4-dimensional being took you and rotated you through that 4th direction and set you back down, you would come back as your mirror image. Your heart on the right. Every organ flipped. The way a letter drawn on glass reads backwards when you turn it over, through the 3rd dimension. H.G. Wells wrote this in 1896, a story about a man thrown into the 4th dimension who comes home with all his insides reversed left to right. Wells was writing fiction, but the geometry underneath it is real. Rotate a 3-dimensional thing through a 4th spatial dimension, and it returns as its own reflection. That's not a ghost story. That's just what the math does. We can't reach the 4th direction, There's no evidence we ever will. But the reason it frightens people isn't that it's impossible. It's that it's so easy. The math doesn't strain. It just quietly points somewhere we can't look and describes, in perfect detail, what could be looking back. Number 9. Kaluza-Klein theory. In the spring of 1919, Albert Einstein opened his mail and found something that unsettled him for the next 20 years. It was a paper from a little-known German mathematician named Theodor Kaluza. And it did something Einstein had been trying and failing to do himself. It took gravity and electricity, two forces that seemed to have nothing to do with each other, and it made them the same thing. Not by adding a new equation, by adding a new dimension. Here's what Kaluza did, and it's almost insultingly simple to describe. Einstein's general relativity is written in 4 dimensions. 3 of space, 1 of time. Gravity, in that picture, is just the bending of those 4 dimensions. Kaluza asked a question nobody had bothered to take seriously. What happens if I write the exact same equations, but in 5 dimensions instead of 4? What falls out? What fell out was electromagnetism. The whole theory of light, and electricity, and magnetism, the equations James Clerk Maxwell had spent his life on, appeared on their own, unasked, as the geometry of that one extra dimension. Gravity was the bending of the 4 dimensions we know, and light was the bending of the 5th. 2 forces, 1 geometry. It was the kind of thing that shouldn't work, and it worked. Einstein sat on the paper for 2 years. That tells you something. He wasn't dismissive. He was rattled. In 1921, he finally presented it to the Prussian Academy of Sciences himself. And for the next 2 decades, into the 1940s, Einstein kept coming back to 5-dimensional ideas in his own work. 8 separate papers. The most famous physicist alive could not let this go. But there was a problem, and it's the same problem that haunts every idea in this video. If there's a 5th dimension, where is it? You don't trip over it. You can't point at it. Kaluza didn't have a good answer. The answer came in 1926 from a Swedish physicist named Oskar Klein, and it's the idea that everything after this depends on. Klein said the 5th dimension is real, and it's everywhere, but it's rolled up, curled into a loop so small you'd never notice it. Picture a garden hose from far away. It looks like a line, 1 dimension. Get close, and you see the line is actually a tube, and an ant on it can walk around the short way. That extra direction was there the whole time. It was just too small to see. Klein figured the 5th dimension curls up at a scale of around 10 to the minus 30 centimeters. Unimaginably tiny. Wrapped around every single point in the space you're sitting in right now. So why isn't this the most famous idea in physics? Because in 1926, it was just too strange. Mathematically, it held together, but a hidden rolled-up dimension at every point in space sounded like nonsense, and physics moved on to quantum mechanics, which was busy being strange in more useful ways. Kaluza and Klein got shelved. And then, half a century later, string theory dug them back up. Because it turned out that if you want to build a universe out of vibrating strings, you don't get to use 4 dimensions. Or 5. You need 10. And the way you hide the extra ones is exactly the trick Klein described. You roll them up too small to see. The idea Einstein couldn't let go of, and then couldn't make work, had been right about the method the whole time. It was just off on the number, and the real number was so much worse. Number 8. Calabi-Yau manifolds. String theory asks you to believe one thing up front, and it's a big one. It says the smallest pieces of reality aren't dots. They're strings. Tiny loops and threads of energy, vibrating, and the note each one plays is what we call a particle. An electron is a string humming one way. A quark is the same kind of string humming another. All of matter, all of force, is one instrument played in different keys. It's a beautiful idea, and it comes with a bill. The bill is dimensions. for the math of string theory to hold together, for the strings to vibrate without the equations tearing themselves apart, the universe cannot have 4 dimensions. It needs 10. 9 of space, 1 of time. We can see 3 of the space ones. So string theory has to explain where the other 6 went. And the answer is the Kaluza-Klein trick from a minute ago, cranked up to something that stops feeling like a trick and starts feeling like a hiding place. The 6 extra dimensions are curled up, folded so small they sit, invisibly, at every point in the space around you. But 6 dimensions don't just roll into a simple loop like Klein's single 5th dimension. 6 dimensions fold into a shape, a specific, intricate, self-intersecting geometric object, and it has a name, a Calabi-Yau manifold. Named after the mathematicians Eugenio Calabi and Xingtung Yau. In 1985, 4 physicists, Candelas, Horowitz, Strominger, and Edward Witten, and remember that last name, he's coming back at number 1, showed that if you fold the extra 6 dimensions into one of these shapes, you can get something that looks a lot like the real world. Now here's the part that should make you a little dizzy. In this picture, the shape of the folded dimensions is not decoration. The shape is the law. The exact way those 6 dimensions are crumpled up at every point in space determines the physics you experience. It sets the mass of the electron. It sets the strength of the forces. It decides what particles can even exist. Change the fold, and you change the rulebook of reality. Let me give you the cleanest example, because it's almost too neat. The number of holes in the Calabi-Yau shape, the higher dimensional version of the holes in a donut, determines how many families of matter particles the universe has. Our universe has exactly 3 families, 3 generations of matter, stacked copies of the same basic particles at heavier and heavier masses, and physicists have never fully understood why 3. String theory's answer is unnervingly simple, because the shape has 3 holes. That's it. The reason you're made of the particles you're made of, instead of some other set, might come down to the number of holes in an object smaller than an atom that you will never see. And now, the part that keeps string theorists up at night. How many possible shapes are there? How many ways can you fold 6 dimensions? The number that gets quoted is 10 to the 500th power. That's a 1 with 500 zeros after it. More possible universes worth of physics than there are atoms in everything we can see, by an almost comical margin. Each fold, a different set of laws, a different mass for the electron, a different strength of gravity. Most of them dead. Most of them universes where nothing can form, nothing can live, nothing can look up and wonder why. And ours is one fold out of that ocean. Some physicists find that thrilling. Some find it a scandal, because a theory that can produce 10 to the 500th different answers starts to feel like a theory that can't be pinned down to any of them. But strip the argument away and sit with the raw idea for a second. The laws of physics, the deepest, most unbreakable rules you know, might just be the shape of a folded thing you can't see. Not a law at all. An accident of geometry. One of 500 zeros worth of ways the dice could have landed. Number 7. The hierarchy problem. Let me show you the weakest thing in the universe. And then let me tell you it might be weak because it's leaking. Take a fridge magnet. A cheap one. The kind holding a takeout menu to your refrigerator. That magnet is holding the menu up against the pull of the entire planet Earth. All of it. Every mountain, every ocean, the whole 6,000 billion tons of rock under your feet, pulling down on that piece of paper. And a magnet you could snap in half wins. A tiny scrap of magnetized metal beats the gravity of an entire world, easily, without trying. We are so used to this that we never stop to feel how insane it is. Gravity runs the universe. It builds the stars. It bends light. It holds galaxies together across distances that would take light 100,000 years to cross. And it is, by an almost unbelievable margin, the weakest force there is. Compared to the electromagnetic force, the one in that fridge magnet, gravity is about 10 to the 40th power times weaker. That's a 4 with 40 zeros after it. 40 orders of magnitude. There is no honest way to make that number feel small. It's one of the biggest, strangest gaps in all of physics, and physicists have a dry little name for it. The hierarchy problem. For most of the last century, nobody had a good answer. Gravity is just weak. That was the shrug. But it bothered people, because 40 orders of magnitude is not the kind of number that usually shows up by accident. Numbers like that usually mean something is going on that you haven't understood yet. And then, in the late 1990s, a group of physicists offered an answer that turns the whole problem inside out. What if gravity isn't actually weak at all? What if gravity is exactly as strong as the other forces? And the reason it looks weak to us is that most of it is escaping somewhere we can't see. Here's the picture. Imagine the other three forces, electromagnetism and the two nuclear forces, are stuck in our 3 dimensions. They run along the surface of our world, trapped, and we feel their full strength. But gravity is different. Gravity, in this idea, isn't trapped. Gravity spreads into the extra dimensions, the folded, hidden ones from the last 2 numbers. And a force that spreads into more dimensions gets diluted. Spread thin. Think of a drop of ink. In a narrow tube, it stays concentrated and dark. Let it spread across a whole swimming pool, and it fades to nearly nothing. Gravity, on this view, is that ink in the pool. It isn't feeble. It's just been shared out across dimensions we're not part of, and what reaches us is the leftover. So when you stand up in the morning and feel your own weight, feel how heavy your arms are, how hard it is to get out of bed, you're not feeling the full force of gravity. You're feeling the fraction of it that stayed in our dimensions. The rest, if this is right, has drained off the edge of the world we can touch, into the space between dimensions. The most familiar sensation you have, your own weight, might be the shadow of a force that mostly lives somewhere else. We don't know if it's true. It might be that gravity is just weak, full stop, and the answer is boring. But that 10 to the 40th gap is still sitting there, unexplained, every time your feet hit the floor. And one of the leading guesses for what it means is that gravity has somewhere else to go. Number 6. Large extra dimensions. So far, every extra dimension in this video has been microscopically small. Klein's 5th dimension, 10 to the minus 30 centimeters. The Calabi-Yau folds, smaller than an atom. That's been the comfort blanket the whole time. Yes, there might be extra dimensions, but they're so unimaginably tiny that they're basically a rounding error. You can sleep at night. Then, in 1998, 3 physicists took the comfort blanket and set it on fire. Their names were Nima Arkani Hamed, Savas Dimopoulos, and Gia Diwali, and the model they built is known by their initials, ADD. They were trying to solve exactly the puzzle we just talked about, why gravity is so absurdly weak. And they took the leaking gravity idea and asked a dangerous follow-up question. If gravity leaks into extra dimensions, how big could those dimensions be before we'd notice? Everyone had assumed the answer was unimaginably small. ADD did the math properly and got a very different answer. The extra dimensions, they found, could be as large as a millimeter. A millimeter. The width of the line at the edge of your fingernail. Not 10 to the minus 30 centimeters. Not smaller than an atom. A distance you can see. A distance you could measure with a decent ruler. Now, stop and let that resettle everything. The reason we assume extra dimensions are safe to ignore is that we picture them as infinitely tiny. ADD said there could be a whole extra direction of space, folded up, sitting at the millimeter scale, threaded through every point of the room you're in. And the reason you've never bumped into it is beautiful and simple. You are made of ordinary particles, electrons, quarks, and ordinary particles are stuck in our three dimensions. They can't enter the extra one. Only gravity can. So the only way to catch a millimeter-sized extra dimension is to measure gravity itself, at very small distances, and look for the moment it stops behaving the way Newton said it should. That's a real experiment. People build them. They're called torsion balance experiments, and they are exquisitely delicate machines. Essentially, very carefully hung weights, watched for the tiniest twist, to test whether gravity between two objects a hair's breadth apart still follows the familiar law. If gravity started leaking into an extra dimension at short range, the pull would get stronger, faster than it should, and the balance would betray it. Physicists have been closing that gap for years. So far, gravity has behaved down well below a millimeter, which has squeezed the original ADD window. But the idea did something that doesn't unhappen. It moved the extra dimensions out of the realm of too small to ever matter, and into the realm of right here, at a scale you can picture, possibly in the space between your fingers as you hold them up. That's the part that lingers. Not that the extra dimension is huge and far away, that it might be small enough to hide, and large enough to be close, sitting quietly at the edge of what our best instruments can feel, in the gap between 1 millimeter and the next. Number 5. The brain world. We keep saying ordinary particles are stuck in our three dimensions. Electrons can't leave, quarks can't leave, you can't leave. I've been saying it like it's a small thing. It is not a small thing. It might be the most claustrophobic idea in all of physics. And in 1999, two physicists gave it a shape. Their names were Lisa Randall and Raman Sundram, and their model has a word attached to it that I want you to sit with. Brain, short for membrane. The idea is this: our entire universe, everything, every star, every galaxy, every atom in your body, every thought you've ever had, is stuck to a membrane, a three-dimensional sheet floating inside a larger space of higher dimensions. And that larger space, the space the membrane floats in, has a name too. It's called the bulk. Picture a soap film stretched across a wire loop. Thin, flat, a two-dimensional surface. Now imagine creatures living inside that film, so flat they've never suspected there's a room around them. The film is their whole universe. The air outside it, the space the film hangs in, that's the bulk, and they can't reach it. They can slide anywhere along the film. They can never step off it. That, Randall and Sundram said, is us. Our universe is the film. The higher dimensional bulk is the room it hangs in, and everything you are is painted onto the surface. Why would everything be stuck to a sheet? Because of the same rule, we've been building all video. The forces that hold you together, the ones that make your atoms atoms, only work along the membrane. They can't reach into the bulk. So the particles they bind are trapped there with them. You are held to the brain by the very forces that make you you. There's no door. There's no edge to walk to. The trapping isn't a wall around the universe. It's woven into every particle you're made of. And gravity is the exception. Again. Gravity is the one thing that can reach off the membrane and into the bulk, which is why Randall and Sundram could use this to explain why gravity is so weak. It's the force that's leaking off our sheet into the room beyond. They built two versions. In the first, there are two membranes with the bulk between them. But it's the second version that I find genuinely hard to shake. In that one, the extra dimension isn't a small gap between two brains. It's infinite. It goes on forever. And yet gravity stays bunched up near our membrane so tightly that, to us, the universe still looks flat and ordinary and four-dimensional. Read that again. There could be an infinite dimension right next to us, starting at the surface we're stuck to and extending outward forever. And we would have no way of knowing. No sensation of it. No instrument pointed the right way. An endless space. A hair's breadth off the surface of everything you can touch. And you are glued to your side of it for the whole of your life, without ever once being able to lean over the edge and look. Number 4. Micro black holes. Everything until now has been theory. Chalk on a board. Beautiful, unnerving, but safely abstract. This is the number where it stopped being abstract, and where, for a little while, some people genuinely believed the extra dimensions were about to end the world. Here's the setup. If the large extra dimensions from number 6 are real, if gravity really does get strong at close range because it's leaking into millimeter scale dimensions, then there's a consequence nobody could ignore. Gravity becomes powerful at much lower energies than we thought. And if you can make gravity strong in a small enough space, you can make the most extreme object in the universe. You can make a black hole. A tiny one. Microscopic. But a black hole. Now, where do you make gravity that concentrated on purpose? You smash particles together as hard as you possibly can. And in the 2000s, humanity built the biggest machine it has ever built to do exactly that. The Large Hadron Collider, a ring 17 miles around, buried under the border of France and Switzerland, designed to slam protons together at very nearly the speed of light. And as it was being switched on, a very simple, very frightening question went public. If extra dimensions are real, could this machine accidentally create a black hole right here on Earth? It went further than a question. In 2008, 2 men filed a lawsuit in federal court in Hawaii to try to stop the collider from being turned on. Their argument was that the people running it hadn't proven it was safe, that it might create a micro black hole, or an exotic clump of matter called a strangelet that could grow and swallow the planet. This actually happened. A machine built to study the origin of mass got taken to court over the fear that it would open a hole in reality. The physicists had an answer, and it rests on a name you know: Stephen Hawking. Back in 1974, Hawking showed that black holes aren't perfectly black. They leak. They radiate energy, slowly evaporating, and the smaller a black hole is, the faster it goes. A microscopic black hole, by this math, wouldn't grow at all. It would evaporate almost the instant it formed, gone in a flash before it could swallow a single extra particle. That's the safety case. That, plus a simpler point, cosmic rays far more energetic than anything the collider produces have been hammering Earth's atmosphere for billions of years, and we're still here. The court threw the lawsuit out, but notice how it did it. It dismissed the case for lack of jurisdiction. Essentially, an American court ruling it had no authority over a machine in Europe. Not on the physics. And the physics safety case has a quiet soft spot, which is this. It leans on Hawking radiation being real. And Hawking radiation, as elegant and widely accepted as it is, has never actually been directly observed. Nobody has ever watched a black hole evaporate. We are almost certainly fine. The collider has run for years and made no black holes at all. But the argument that reassured everyone was built on a piece of physics we still have not seen with our own eyes. The safety net was theoretical. We just really, really hope the theory holds. Number 3. Shadow matter. Let me tell you about the single biggest embarrassment in modern astronomy, and then let me tell you the most disturbing explanation for it. When we look at galaxies, they spin wrong. The stars at the edges move far too fast. By every law we trust, a galaxy spinning that quickly should fling its outer stars off into the dark, like mud off a fast wheel. They should not stay, but they stay. Every galaxy we've measured does this, and the only way to make the math work is to say there's extra matter there, a huge amount of it, that we cannot see. Matter that has gravity, but gives off no light. We call it dark matter, and it's not a small correction. there's roughly 5 times more of it than all the ordinary matter in the universe. 5 times more than every star, every planet, every cloud of gas, every living thing. The universe we can see is the minority. Most of it is invisible, and we do not know what it is. The usual guess is that dark matter is some new kind of shy particle, drifting through everything, barely interacting. Maybe. But there's another explanation, and it comes straight out of everything we've built in this video, and it is so much stranger. What if dark matter isn't a weird new particle at all? What if it's completely ordinary matter? The same protons, the same electrons, the same kind of stuff you're made of, but living on a different brane. Remember the brane world. Our universe stuck to a membrane, floating in the bulk. Now imagine ours isn't the only membrane. Imagine there's another one, parallel to ours, a whisper away in the bulk. And on that other sheet, there's a whole other world. Its own matter, its own forces, possibly its own stars, its own galaxies, its own structure. And here's why we'd never see it. Light can't cross the gap between branes. Their light stays on their sheet. Our light stays on ours. The only thing that reaches across the bulk, the only thing that leaks from one membrane to the other, is gravity. So from our side, we'd feel it. We'd feel the pull of all that hidden matter, tugging on our galaxies, holding our fast-spinning stars in place. But we'd never see a single point of its light, because its light was never ours to see. It would look to us exactly like dark matter, an invisible mass, felt only through gravity. This idea has a family of names: shadow matter, mirror matter, and the mirror version goes back to 1966. In the string theory framing, the two worlds are simply two parallel branes, with gravity crossing the space between them. Sit in that for a second. If this is right, then most of the matter in the universe isn't strange at all. It's a parallel world, overlapping ours, sharing the same space you're sitting in, one dimension over, going about its business, made of its own version of everything. There could be a shadow sun, a shadow earth. It sounds like a fever dream, and it might be wrong. But every galaxy in the sky is spinning too fast to hold itself together, and one of the serious answers on the table is that you are not alone in this room. You're just separated from what's here by a direction you can't turn your head to face. Number 2, the ekpyrotic universe. Ask where everything came from, and you'll get one word: the Big Bang. 13.8 billion years ago, the entire universe, everything, erupts out of a single point, and time itself begins. That's the story we all grew up with, and it's a good story. But there's a question inside it that we usually tiptoe past. What banged? What was there to explode? What set it off? The standard story mostly answers with a shrug and a warning that the question might not even make sense. In 2001, 4 physicists offered a different answer, and it lives entirely in the space between dimensions. The names are Justin Corey, Bert Everett, Paul Steinhardt, and Neil Turok. And they said this: the Big Bang was not the beginning. The Big Bang was a collision. 2 branes, 2 of those membrane universes, floating in the higher dimensional bulk, drifted toward each other and slammed together. And the unimaginable energy released in that impact, spread across the whole surface of the membrane at once, is what we experience, looking back, as the Big Bang. Not an explosion from a point. A collision across a sheet. They named it the ekpyrotic universe. The word comes from ancient Greek, ekpyrosis, meaning conflagration, a great fire. It's borrowed from the old Stoic philosophers, who believed the universe was born in fire, died in fire, and was reborn again, over and over, forever. And the physicists chose that word on purpose, because their model has a version that does exactly that. In the cyclic version, the 2 branes don't collide just once. They collide bounce apart, drift, and are pulled back together and collide again, over and over. Roughly every trillion years, the brains touch, and a new Big Bang lights up across the sheet. A new universe, a new run of stars and galaxies, and maybe a new set of people looking up and asking where it all came from. Here's what that does to the timeline in your head. In the standard story, our Big Bang is the beginning of time. Before it, there is no before. The question is banned. But if the ekpyrotic picture is right, time did not begin at our Big Bang. There were universes before ours, trillions of years of them. Our Big Bang was just the most recent time two membranes touched. One flash in a sequence that stretches back with no clear start and forward with no clear end. And then there's the part I can't quite put down. If the brains collide on a cycle, if the next collision is simply a matter of the two sheets drifting back into contact, then nothing in the physics says it can't happen again. There's no rule that reserves the next Big Bang for a trillion years from now. The membranes move through the bulk on their own schedule, in a direction we cannot see, and we, stuck flat on our sheet, would have no way to watch them approach. No warning light, no sky going strange. Just, at some moment, we could never predict, the far surface of another universe arriving. It is almost certainly nothing you or anyone you'll ever know needs to worry about. But the idea that our beginning was a collision, and that collisions, by their nature, can happen more than once. That's the kind of thought that changes the texture of a quiet night. Number 1. The 11th dimension. We've been climbing a ladder this whole time, and we didn't say so. One hidden dimension with Kaluza and Klein. 6 more folded into a Calabi-Yau shape for string theory. Membranes floating in a bulk. Every step added dimensions, and every step the people building it thought they were near the top. And then, in 1995, a man walked into a conference and knocked the top off the ladder. His name is Edward Witten, and he is, by wide agreement, the most formidable mathematical physicist alive. In the mid-1990s, string theory was in a quiet crisis. It was supposed to be the one theory of everything, and instead, there were 5 different versions of it. 5 separate competing string theories, each internally consistent, each claiming to describe reality, and no way to tell which was right. 5 theories of everything is 4 too many. It looked like a dead end. Witten stood up at a conference in 1995 and said something that reorganized the entire field. The 5 theories aren't competitors. They're the same theory, seen from 5 different angles. They're 5 shadows of one deeper thing. And that deeper thing does not live in 10 dimensions. It lives in 11. 10 of space, 1 of time. He called it M-theory. And this launched what physicists now call the second superstring revolution. That 11th dimension is the punchline of everything in this video. Because down in 11 dimensions, the objects aren't just strings anymore. There are membranes, brains, sheets, and higher dimensional surfaces, all living together in this 11-dimensional space. Everything we've talked about, the brain worlds, the parallel sheets, the collisions, all of it finds its home here, in the deepest layer, in the bulk of M-theory. This is the floor the whole building stands on, and it's the floor we can never reach. Here's the vision if M-theory is right. Our entire universe, the brain world, the membrane we're painted onto, is one sheet among possibly countless others, all of them floating in that 11-dimensional space. Every parallel universe, every other world, a separate brain, stacked and drifting in a bulk that we, trapped in our 3 visible dimensions, have no way to perceive. Not because it's far away. Because it's in directions our bodies, our instruments, our imaginations were never built to face. The most complete picture of reality we have ever assembled describes a place, and then tells us we can never go there, and can never see it, and may never be able to prove it exists. because that's the last, sharpest edge of all of this. Witten never even said what the M stands for. He left it open, magic, mystery, or membrane, he said, according to taste. And more than that, M theory, for all its beauty, still has no complete formulation. No one has ever written the whole thing down, and it has never made a single prediction we've been able to test. It might be the deepest truth about existence. It might be a magnificent piece of mathematics that reality politely declines to obey. And we may never know which, because the answer is written in dimensions we are physically incapable of entering. So here's where all of this leaves us. We are three-dimensional creatures, glued to a membrane, feeling only the fraction of gravity that didn't escape, staring at a sky full of matter we can't see, born maybe from a collision we can't remember, inside a reality that our best theories say is 11 dimensions deep and mostly, permanently, out of reach. We built the entire map, and the most honest thing on it is the edge, where the roads stop and the label just reads, "We cannot go there. Not yet. Maybe not ever." But we drew the edge anyway, and we keep leaning toward it, in a direction we can't quite turn to face, trying to see what's on the other side. Thank you for watching and sticking till the end. We've got plenty more videos coming in the future. Hit that subscribe button so you don't miss them. See you in the next one.